Our oceans cover more than 70% of our planet, supporting life in ways we're only beginning to understand. But beneath the surface, an invisible transformation is unfolding, one that has profound implications for marine life and, in long term, humans too. Ocean acidification is a complex, often overlooked process with the power to reshape marine ecosystems, impact human communities, and challenge the stability of our global environment.
First, we must ask, what exactly is ocean acidification? To put it simply, it's the gradual increase in the acidity of our oceans, largely due to human-driven carbon emissions. When carbon dioxide, CO2, is released into the atmosphere, the oceans absorb about a third of it, setting off a chain of chemical reactions causing the ocean to become more acidic. When CO2 enters seawater, it forms carbonic acid. This acid then breaks down, releasing hydrogen ions, which in turn increases the water's acidity. These reactions deplete essential carbonate ions, which many marine species depend on to build their shells and skeletons.
From microscopic plankton to vast coral reefs, life underwater relies on extremely delicate balances. Ocean acidification shifts these balances, creating a cascade of changes that threaten the very foundation of marine ecosystems. Imagine a line of dominoes. The first domino falls by the hand of mankind. The first domino that sits off the chain is the emission of carbon dioxide into the air. This hits the second domino, causing ocean acidification. Then, this domino number 3, shellfish or any other certain kind of animal, goes extinct because they cannot survive in acidic water. This domino hits domino number 4, the disruption of the food chain. Soon, other animals that eat shellfish will starve, resulting in mass extinction. Thus, this imaginary line of dominoes shows how easily ocean acidification can cause an unstoppable chain of events that will ultimately destroy our oceans.
Since the start of the Industrial Revolution, the pH of our ocean surface waters has decreased by about 0.1 units, representing a 30% increase in acidity. This may sound small, but even small changes in pH can have a dramatic effect on marine organisms.
Ocean acidification significantly affects marine organisms, particularly those that rely on calcium carbonate for their shells and skeletons. Species such as coral, mollusks, and some plankton are among the most vulnerable.
Corals are especially impacted by acidification. As acidity increases, corals struggle to absorb the carbonate ions they need to build their calcium carbonate skeletons. This not only weakens the corals, but also makes them more susceptible to bleaching and disease. According to a Catalyst Planet, the Great Barrier Reef could be completely dead by 2050.
The implications of ocean acidification extend beyond marine life. The health of our oceans is closely tied to the entire global climate. Healthy oceans regulate temperature, produce oxygen, and sequester carbon dioxide, all vital for a stable climate. Ocean acidification can cause a chain reaction that will affect the entire global climate.
Coastal communities that depend on fishing and tourism are already feeling the effects. As fish populations decline and coral reefs die, economic stability is threatened, putting entire communities at risk.
In addition, ocean acidification can impact ocean circulation patterns, which in turn affect weather systems and climate regulation. The health of our oceans is integral to the health of our planet as a whole.
So, what are the primary causes of ocean acidification? Well, the primary driver is the increased carbon dioxide emissions from human activities, including the burning of fossil fuels. Deforestation also plays a role by reducing the number of trees that absorb CO2. Thus, more CO2 goes into the ocean than getting absorbed by trees.
Okay, so we've gone over what it is, its impacts, and its causes. Now, we need to know how to prevent it. So let's do some science. I'm here in Chatham, Massachusetts to measure the acidity of the Atlantic Ocean. Now, it's very important to note exactly what my location is, because if I'm located near a major industrial hub, the water might be significantly more acidic. If I'm near a wildlife preserve, it might be significantly less acidic. Right now, I'm in Chatham, Massachusetts, and there's a wildlife preserve about a mile that direction, and there's relatively no pollution going into the water around here. So what I'm gonna do is I'm gonna measure this, with this pH strip into this water right here, and I'm gonna basically measure it with the help of this guide right here, along with some other very similar things, and I'll come back to you. So what I'm gonna do is I'm gonna walk into this water, right? And then I'm going to measure around for 3 seconds. Okay, so now I'm gonna take these results and measure them, and then we'll figure out exactly how acidic the water is. So just to show what's being shown on this strip here, on the top here we have the monopersulfate scale, on the middle we have alkalinity, and then on the bottom is what we actually are here for, which is the pH scale. I'm now in Marco Island, Florida. To take note of my location once again, the Everglades are right over there. Now that's very important because the Everglades, which are one of the largest natural preserves in our entire country, host hundreds and hundreds of millions of trees. Now that's very important because those trees are sucking up all the CO2 in the water and atmosphere and turning it into oxygen, which means that theoretically the water right here is going to be significantly less acidic than Chatham, Massachusetts. I have some more pH strips here to test it, and that's exactly what I'm going to do right now. So again, I'm going to do the same thing that I did in Cape Cod. Now this is what they look like. And now we can actually compare that to the chart here. Here's the chart. Oh, here it is. So the pH is actually pretty red, which means it's actually somewhat good here. It's around 7.8 or 8.4. So that means it's actually kind of healthy here. Now that makes sense because the Everglades are over there and all of those trees are absorbing CO2. So essentially all the Everglades, since there's millions and millions of trees, are absorbing all of the CO2, and it's actually making the ocean less acidic, which is one of the reasons why deforestation is one of the biggest issues when it comes to ocean acidification. Because as you can see, the pH is actually pretty good here. Now, to compare the results from Chatham to Florida, the results in Chatham measured in around 7.3 on the pH scale. Here, they measured in around 7.8. Now, these are both relatively good numbers because they're still relatively neutral on the pH scale, as it's neutral at 7. However, Chatham, Massachusetts was significantly more acidic. And this is due to the fact that Chatham, Massachusetts doesn't really have many forests or plant life to suck up all the CO2. Here in Florida, there's the Everglades, and that's a very big factor. Therefore, we see that places with a lot of greenery and wildlife have a significantly less acidic ocean. So 2 things that we can take away from this experiment are 1, that the ocean is significantly less acidic in places with a lot of wildlife, for example, the Everglades. And 2, that deforestation is one of the biggest issues when it comes to ocean acidification. Because if places like the Everglades are destroyed, there's nothing to protect the ocean from becoming more acidic. And with that, let's get back to the video.
So what we see is that the ocean is generally less acidic around nature preserves and national parks. We see that it is significantly more acidic in industrial centers with a large CO2 output. Therefore, Reducing greenhouse gas emissions is the most direct way to combat ocean acidification. Transitioning to renewable energy, improving energy efficiency, restoring forests, and supporting sustainable industries can help reduce the acidity in oceans.
While large-scale policy changes and technological advances are essential, individual actions such as using less energy, choosing sustainability sourced seafood, and educating others also contribute. Collective efforts, both small and large, can slow the rate of ocean acidification and give marine life a chance to adapt.
We suggest that Congress pushes for stronger climate change legislation. By placing a price on carbon emissions, Congress can push industries to adapt cleaner technologies and reduce emissions. A carbon tax would directly make fossil fuels more expensive, encouraging both individuals and corporations to transition to cleaner energy sources. A cap-and-trade system would set a limit on total emissions and allow businesses to buy and sell emissions allowances, providing flexibility in how to reduce emissions.
Congress can encourage the development and deployment of renewable energy sources like solar, wind, and geothermal, and energy-efficient technologies. By accelerating the transition to a low-carbon economy, the U.S. and other governments can significantly reduce the atmospheric CO2 that contributes to ocean acidification.